In this video, I will talk about overfitting and underfitting. Overfitting is also referred to as variance in machine learning, and underfitting is sometimes referred to as bias. And this issue of overfitting versus underfitting is also known as the bias variance trade-off. The bias variance trade-off. Now, this, it turns out, is a central problem in supervised learning, in any supervised learning. So you can imagine overfitting and underfitting, or high bias and high variance, as like a tug of war between two. So maybe one party is trying to overfit and the other party is trying to underfit. Now, conceptually, what underfitting means is, say you have a data set, right? A data set, and let's say the data has 1,000 patterns, 1,000 patterns in the data. If your model is small model or a model with very low capacity, and it only, let's say, learns 10 of the 1,000 patterns, then the model is said to underfit. That is, it does not fit the data set. It has very high bias. Similarly, overfitting is the case when, let's say, for example, here's our data set, and let's say it has same 1,000 patterns, right? 1,000 patterns in the data. And what your model does is, it doesn't just learn this 1,000 pattern, but it starts memorizing. Let's say we actually have 100,000 examples, right? And then we have 1,000 patterns that we want the model to learn. But let's say instead of learning these 10,000 pattern, it looks at all the 100,000 example and it starts memorizing the data sets such that it knows exactly what output to predict given these 100,000 examples. So it doesn't consider these patterns that it has to learn, but instead focuses on memorizing these 100,000 examples such that given any of these 100,000 examples, it will do very well on these 100,000 examples. But given a new data set, it may not do so well because it's focusing on memorizing these 100,000 examples. Now, high bias basically is too less optimization. Now, if we remember the 6 blind men story, here the picture summarizes that, then this is similar to having too few blind people. So say in this data set of elephant, let's say we actually have more than 6 patterns, but let's say these 6 patterns are what we are looking for, right? Then high bias is the case when we have too few blind people. That is, our model misses to learn many representative training data sets. Now, similarly, high variance, on the other hand, is too much optimization. And this is similar to having too many blind people. And the model learns unrepresentative training data as well. So imagine if we had maybe 100 blind people touching the elephant and coming up with 100 different theories about how an elephant looks like. So what do we want? Do we want high bias or do we want high variance? Interestingly, we don't want either. Instead, what we want is generalization. That is, we want the model to learn these 1,000 patterns, common 1,000 patterns that are common among the data sets, common in the entire data set. So going back to the blind man and the elephant example, when we say we want generalization, what we want is we want a few but smart blind people. We don't want blind people that just look at one side of the elephant or one particular aspect of the elephant, but maybe a few blind people who can say something like this: one side is a snake-like and the other side is rope-like. So we want blind people who can do this bigger picture sort of assessments about the data and learn more general patterns in the data. So that's the goal in training these machine learning models. We want a model that sits right in the middle of the bias and variance trade-off, very well balanced with a good balance of underfitting and overfitting such that it generalizes as much as possible.